Welcome back, everyone, for another deep dive.
Excited to be here.
This time, we're going on a thrilling ride, exploring something truly vital to space exploration, spacecraft shielding.
Yeah, it's one of those things you don't always think about.
Right. But it's absolutely crucial for protecting our spacecraft and, of course, the astronauts inside from all the dangers lurking out there in space.
Absolutely.
We're talking micrometeoroids, orbital debris, intense radiation, extreme temperatures.
It's a wild and unforgiving environment out there.
It is. And to guide us through this complex world, I've got a stack of fascinating scientific journals and some really cool YouTube videos.
Nice. A mix of the technical and the visual. I like it.
Exactly. We'll get the full picture from the nitty-gritty science to some mind-blowing visuals. So are you ready to dive in?
Absolutely. Let's go.
All right. Let's start with, something that sounds kind of scary, but also really fascinating.
Okay. I'm intrigued.
Okay, so picture this. Tiny particles of space debris, like little bits of rock or metal, zipping through the void at incredible speeds.
Yeah, like microscopic bullets.
Exactly. And even a tiny speck, like a flick of paint, traveling at tens of kilometers per second, can cause serious damage to a spacecraft.
Oh, absolutely. It's a major concern.
So how do we even begin to protect our spacecraft from these microscopic bullets? It seems like an impossible task.
Well, that's where the ingenious design of the Whipple shield comes in.
Whipple shield. Tell me more.
So imagine a shield that's, well, not designed to completely stop a projectile head on. Instead, it's meant to shatter it.
Shatter it.
Yeah, it breaks that incoming projectile into a cloud of smaller, less harmful fragments.
Oh, I see. So it's not about stopping it dead in its tracks. It's about kind of diffusing the impact.
Precisely. And the Whipple shield does that with multiple layers. That first outer layer is like the disruptor.
Okay, the disrupt.
Then you have a spaced rear wall, which acts like a second line of defense.
Mm.
And it absorbs the energy from those dispersed fragments.
So it's a 1-2 punch. First disrupt, then absorb. That's pretty clever.
It is. It's a pretty ingenious system that's been incredibly effective.
It is. Now, I was looking through our research, and I came across some pretty intimidating equations.
Oh yeah, there's definitely some serious math involved.
There is things like NO, mod N,
Yeah.
and JSC Whipple. Are those just for show, or do they actually mean something?
Oh, they definitely mean something. Those are, think of them like the secret sauce, the mathematical recipes that engineers use to predict how a Whipple shield will perform under different conditions.
Makes sense.
Like the size and speed of the incoming debris, even the angle of impact, all those things factor in.
So it's not just like slapping some metal plates together and hoping for the best. There's a lot of science and math behind these seemingly simple shields.
Absolutely. There's a lot of thought and testing that goes into designing these shields to make sure they're as effective as possible.
Wow. That's impressive.
And speaking of testing, that JSC Whipple equation you mentioned.
Yeah.
Well, that one was developed based on years of testing at NASA's Johnson Space Center.
Oh, wow.
And they used a massive database of over 1,135 impact experiments.
Over 1,000 tests. That's
Right.
dedication.
Yeah. So you can see why they trust it to predict how well a shield will work in a real world scenario.
Makes sense. Now, speaking of seeing these shields in action,
Yeah.
I stumbled upon this really cool YouTube video from Lockheed Martin. It shows the heat shield protecting the Mars Perseverance rover during its descent to Mars.
Yes, the aeroshell. It's an amazing piece of engineering.
It is. It's designed for atmospheric entry, of course, but it shows in a really visual way how this multi-layered protection works,
Right. It's all about those layers, spaced apart, to dissipate intense heat and energy, just like a Whipple shield, but for a different kind of threat.
Exactly. So similar principles, but applied to a different challenge. It's fascinating how that same basic idea can be used in so many different ways in space exploration.
Yeah, it's a testament to how creative engineers have to be when solving problems in space.
It is. Now, I have a question about the materials used in these shields. Are we stuck with just aluminum, or are there other materials that could do the job maybe even better?
That's a great question.
Yeah.
And the answer is a definite no.
Mm-hmm.
We're not limited to just aluminum. Researchers are always looking for new and innovative materials for spacecraft shielding.
Oh, cool. Like what?
Well, one really promising area is composite materials.
Composites,
Yeah.
like carbon fiber. Isn't that what they use in race cars and airplanes?
Exactly. And it turns out that composites offer some pretty unique advantages for spacecraft as well.
Oh, interesting.
Yeah. For one thing, they can be much lighter than traditional aluminum while still being incredibly strong.
Okay, lighter and stronger. I like where this is going.
And here's the kicker.
Yeah.
Some composites can even provide better radiation shielding.
Wait, so we could potentially have a shield that's lighter, stronger. A&D offers better protection against radiation. That's like winning the space shielding lottery.
It's pretty amazing, right?
It is. So what kind of composites are we talking about here?
Well, there are a few different types being explored. Carbon fiber reinforced polymers, or CFRPs, are a popular choice.
TFRPs?
Yeah. And researchers are experimenting with different resins to enhance their properties,
Yeah.
to tweak their performance.
So it's like baking a cosmic cake, trying to find the perfect mix of ingredients for ultimate shielding power.
I like that analogy. You're spot on.
Thanks. So, did they find a winner in their tests? Was there a particular composite that really stood out?
Actually, yeah, there was one that performed particularly well. Out of all the composites they tested, a specific mix of polypropylene and silicon carbide powder, or SiC, provided the highest dose reduction rates.
Polypropylene, isn't that what they make those reusable shopping bags out of?
You know your materials. That's exactly it. But it just goes to show that, sometimes the most unexpected materials can lead to incredible breakthroughs in space technology.
That's so cool. And it makes me even more excited to talk about radiation shielding itself, because it's one of those invisible dangers that we don't always think about, but it's a big deal in space, right?
Absolutely. Radiation is a major concern for astronauts, especially on long-duration missions. Think about a mission to Mars, for example.
Right.
The radiation exposure out there is significantly higher than here on Earth.
I read somewhere that a trip to Mars is the equivalent of getting a full-body CT scan every 5 or 6 days.
Yeah, that's about right. It's a
Yeah.
lot of radiation exposure, and over time, it can have some serious health consequences. So yeah, not good.
So researchers are constantly looking for ways to create better ways to protect astronauts from this invisible threat.
Makes sense. So what are some of the ideas they're exploring? How do you even shield against something that you can't see or touch?
Well, one idea that's really captured my imagination is the concept of an artificial magnetosphere.
An artificial magnetosphere. Okay, now that sounds like something straight out of Star Trek. Is that even possible?
It might sound like science fiction, but the science behind it is actually quite sound.
Okay.
So you know how Earth has a natural magnetosphere?
Right, it's like a magnetic bubble that protects us from harmful radiation from the sun.
Exactly. And well, the idea is to create a similar kind of protective bubble around a spacecraft, or even potentially around an entire planet like Mars.
Wow, that's ambitious. But how do you create a magnetic field in space? Do you launch a giant magnet into orbit? Well, one idea involves positioning a powerful magnetic shield at a specific point between the Sun and Mars, called the Sun-Mars L1 Lagrange point.
A Lagrange point. I'm going to need a bit more explanation on that one.
Sure. So imagine this. The Sun and Mars are in a sort of cosmic dance, constantly pulling on each other with their gravity. Lagrange points are like special spots in this dance floor where the gravitational forces and the centrifugal force of an object orbiting those bodies, well, they all balance out.
Oh, okay. So it's like a gravitational sweet spot where an object can just, hang out without being pulled in one direction or the other.
Exactly. It's a point of gravitational equilibrium.
I think I'm getting it.
And the L1 point specifically is it's located between the Sun and Mars, which makes it an ideal spot for a magnetic shield. If we could position a powerful enough magnet there, it could potentially deflect a significant portion of the solar radiation heading towards Mars.
So it's like giving Mars its own mini magnetosphere.
That's the idea. It's a pretty ambitious concept, but the potential benefits are huge,
It would certainly make colonizing Mars a lot easier if we didn't have to worry so much about radiation exposure.
Right, but it's important to remember that it wouldn't be a perfect solution. It would offer significant protection against solar radiation, but it wouldn't protect against all types of radiation.
Right. There are still those pesky cosmic rays coming from outside our solar system, and those are a lot harder to block, aren't they?
They are. They're much more energetic and penetrating.
So what are our options for dealing with those? Are there any any solutions on the horizon?
There are some really interesting ideas being explored, and one that I find particularly fascinating is the use of superconducting magnets for radiation shielding.
Superconducting magnets. Okay, now we're talking serious sci-fi tech. I'm picturing like glowing rings and force fields around our spacecraft.
Well, you're not far off.
Mm.
Superconducting magnets have the potential to revolutionize radiation shielding.
Yeah.
They can generate incredibly powerful magnetic fields while using very little energy.
And that's crucial in space, right? Where every watt counts.
Absolutely.
So how would these magnets actually work as a shield? Would they like create some kind of invisible barrier around the spacecraft?
That's the general idea. There are a few different concepts being explored. One involves creating a toroidal magnetic field, which is essentially a donut-shaped field that surrounds the spacecraft.
Okay, a donut-shaped field. I think I can picture that.
Yeah. Another concept involves using a solenoid, which is basically a cylindrical coil that generates a magnetic field along its axis.
So it's like wrapping the spacecraft in a magnetic cocoon.
Exactly. And then there's the field reverse configuration, which is, well, a more complex arrangement of magnets that creates a closed magnetic field, almost like a bubble around the spacecraft.
Okay, that one's a little harder to visualize.
Yeah, it's a bit more complicated,
Yeah.
but all of these concepts have the potential to provide much better protection against cosmic rays than anything we have today.
It sounds very promising. But is it practical? I mean, are superconducting magnets even feasible for space applications? They sound pretty high tech.
That's the challenge. Superconducting magnets require extremely low temperatures to function. Like just a few degrees above absolute zero.
Yeah, that's cold.
It is, which means you need sophisticated cryogenic systems to keep them that cold, and that adds complexity and weight to the spacecraft.
I see. So it's a trade-off. You get this incredible shielding capability, but you have to pay the price in terms of extra equipment and energy requirements.
Exactly, it's a constant balancing act in spacecraft design. You're weighing the benefits against the costs and the limitations.
Right. It sounds like designing these magnetic shields is a pretty delicate process.
It is. You have to optimize for strength, size, weight, energy consumption.
Yeah.
It's a lot to juggle.
It sounds like it. And it's not just about, the shield itself, right? You have to think about how it will integrate with all the other systems on the spacecraft.
Absolutely. And how it will perform in the harsh environment of space.
Right. It's like a giant puzzle figuring out how to fit all the pieces together in a way that works.
Exactly. And speaking of puzzles, you won't believe some of the other creative solutions engineers are exploring for spacecraft shielding.
Oh, okay. Now you've got me really curious. What else is in store?
Well, have you ever heard of origami?
Origami, like the paper folding art. What does it have to do with spacecraft shielding?
It's more connected than you might think. Remember how we talked about minimizing weight and volume in space?
Yeah.
Well, researchers are exploring how to use origami principles to create deployable multi-layered shields.
So instead of launching a big bulky shield, you could fold it up nice and compact and then unfold it once you're in space. That's brilliant.
It is, right. It's like a pop-up tent for spacecraft. And,
Yeah.
and the best part is these origami shields aren't just compact. They could potentially be even more effective than traditional Whipple shields.
Really? So you get better protection and you save on weight and space. That's a win-win.
It is. And there's actual research backing this up.
Wow. How does it even work?
The basic principle is to use folds and creases, to create a structure that can expand and contract, much like an origami crane.
That's incredible. I never would have thought of that. It's amazing how a centuries-old art form can be applied to cutting-edge space technology.
It is. And there are actual tests being done. One study, they tested an origami shield against a conventional Whipple shield of the same mass. And guess what? The origami shield performs significantly better at stopping simulated micrometeoroid impacts.
Wow. That's amazing.
It is. It really highlights the ingenuity and the outside-the-box thinking that's going on in this field.
This is incredible. And to think this is just the beginning, right? There's so much more to explore in the world of of spacecraft shielding?
Oh, absolutely. We've only just scratched the surface.
I can't wait to dive deeper.
Me too.
Ah,
Welcome back to our deep dive into spacecraft shielding.
it's amazing to think that we've only just scratched the surface of how we protect our spacecraft from all those hazards out there.
And it really is.
Uh-huh.
And as we hinted before the break, we're about to enter a whole new realm of challenges with thermal protection.
Right, because space isn't exactly known for its mild temperatures.
You got that right.
It's either boiling hot or freezing cold, depending on where you are, and whether the sun is shining on you or not.
Yeah, it's all about extremes out there.
It is. So how do engineers even begin to design spacecraft to handle these crazy temperature swings?
Well, it all starts with understanding the physics of heat transfer.
Yeah.
You might remember from science class that heat can travel in three ways: conduction, convection, and radiation.
Okay, yeah. I vaguely remember those terms. Conduction is like when heat moves through direct contact, right? Like when you touch a hot pan.
Exactly.
And then convection is about heat spreading through fluids, like how boiling water circulates heat.
Right.
And radiation is heat traveling as electromagnetic waves, like the warmth we feel from the sun.
You got it. You're remembering it all. And here's the thing. In the vacuum of space, convection is pretty much out of the picture.
Oh, big yeah.
There's no air to circulate the heat.
Right. So we can cross that one off our list. But what about conduction? Wouldn't that be a problem if, say, a hot engine came into direct contact with, I don't know, a sensitive instrument or something?
Oh, absolutely. That's a big concern, and that's why spacecraft designers use special materials and techniques to minimize heat transfer through conduction, to keep those hot spots away from the sensitive stuff.
Okay, makes sense. But what about radiation? I mean, how do you even shield against something that can just, zip through empty space like it's nothing?
That's where things get really ingenious. One of the most effective ways to protect against heat radiation is to use multi-layer insulation, or MLI for short.
MLI. Okay, I'm drawing a blank on that one.
Imagine wrapping your spacecraft in a super high-tech space blanket.
A space blanket?
Yeah. That's essentially what MLI is. It's made up of multiple layers of thin reflective material, often aluminized mylar or Kapton, with a vacuum in between each layer.
Wait, so it's all about the layers. What's so special about having all those layers with nothing in between?
That vacuum is the key, because there's no air to conduct heat. The only way heat can move through MLI is by radiation. And that's where those reflective layers come into play.
So they're like tiny mirrors bouncing the heat radiation back and forth until it eventually loses energy.
Exactly. It's remarkably efficient at preventing heat from either entering or escaping the spacecraft.
Okay, that's pretty cool. So it's all about maintaining that delicate balance, right? Keeping the spacecraft at just the right temperature.
Exactly. It's a constant balancing act.
But here's another thought. Spacecraft aren't just, absorbing heat from the outside. They're also generating their own heat internally, right?
Oh, you're absolutely right. All those electronics, all those instruments, they generate a significant amount of heat.
Right. So engineers also have to figure out how to manage and get rid of that heat as well, right?
They do. It's another crucial part of thermal control. You got to prevent the spacecraft from getting too cold from the surrounding environment, but also prevent it from overheating from its own internal systems,
Yeah, that's a tough balancing act.
It is. And one of the most common ways to deal with internal heat is through radiators.
Radiators, like the ones we have in our homes.
Similar concept, but instead of releasing heat into the air, spacecraft radiators release heat into the vacuum of space.
Oh, okay. So it's like having a giant cooling fin attached to your spacecraft. I've definitely seen pictures of those on the International Space Station.
Exactly. Those are radiators, and
Yeah.
they're carefully designed to maximize their surface area, which allows them to radiate heat more effectively. But of course, there's a trade-off, right? The larger the radiator, the more weight it adds to the spacecraft.
Right. Always a compromise.
Always. And it's not just about the size of the radiator. The orientation of the spacecraft also plays a crucial role in thermal control.
Orientation. How does that come into play?
Well, imagine a spacecraft orbiting Earth. If one side is constantly facing the sun, it's going to absorb a lot more heat than the side that's facing away, right?
Oh, right, right. So it's like trying to get a tan at the beach. You have to keep rotating so you don't get burned on one side.
Exactly. And engineers use a similar strategy with spacecraft. They carefully plan the spacecraft's orientation and even its rotation to control how much heat it absorbs from the sun.
So it's like choreographing a cosmic dance, making sure the spacecraft is always in the right position to maintain a stable temperature.
That's a great way to put it. And this becomes even more important when you consider that spacecraft often move through different thermal environments, you know?
Oh. Right, like
Yeah.
like going from the bright sunlight of Earth orbit to the shadowy depths of deep space as they travel to another planet or something.
Exactly. So the
Yeah.
the thermal control system has to be adaptable and able to adjust to those changing conditions.
Wow, this is way more complicated than I ever imagined.
It is, but engineers have a few more tricks up their sleeves.
Yeah.
Have you ever heard of heat pipes?
Heat pipes. The name rings a bell, but I can't quite place it.
They're pretty fascinating devices. They can transfer heat very efficiently from one point to another.
Okay.
They're often used to move heat away from sensitive components or to distribute it more evenly throughout the spacecraft.
Okay, I'm intrigued. How do they work? Is it some kind of magic?
Not magic, but it's pretty close. Heat pipes are basically they're sealed tubes,
Yeah. Yeah.
and they contain a small amount of fluid. And when one end of the tube is heated, the fluid at that end evaporates and it absorbs the heat.
So the fluid acts like a tiny sponge, soaking up the excess heat.
Precisely. And because it's in a sealed tube, that vaporized fluid travels to the cooler end of the tube where it condenses back into a liquid and releases the heat it absorbs.
So it's like a continuous cycle of evaporation and condensation, moving heat from hot spots to cooler areas.
You got it. Heat pipes they're incredibly efficient and reliable, which makes them ideal for space applications.
That's amazing. It's like a miniature plumbing system for heat. But we've been talking a lot about, spacecraft. What about the astronauts themselves? How are they protected from the extreme temperatures?
Well, astronauts have their own personal thermal control systems.
Yeah.
Their spacesuits.
Right. Spacesuits. I've always been fascinated by those things. They're like mini spacecraft themselves, keeping astronauts alive and comfortable in the harshest environment imaginable.
They are. They're incredible feats of engineering. They have to provide everything an astronaut needs to survive in space, oxygen, pressure regulation, communication systems, and of course, temperature control.
It's mind-boggling to think about all that technology packed into those suits.
It is. And when it comes to thermal control, spacesuits use a combination of insulation, liquid cooling, and even heating elements to keep the astronaut at a comfortable temperature no matter what's going on outside.
So it's like a personalized climate control system, keeping astronauts from turning into popsicles or overheating.
That's the idea. The spacesuit is constantly monitoring the astronaut's body temperature and adjusting the heating and cooling as needed.
Yeah, that's incredible. It's amazing to think about all the technology that goes into, keeping humans alive and functioning in such an unforgiving environment.
It's really remarkable. And as we wrap up this segment on thermal protection, it's important to remember that this is just one piece of the puzzle when it comes to spacecraft shielding.
Right. We've covered a lot of ground here. Whipple shields, origami-inspired designs, the intricacies of heat pipes and spacesuits.
We have. It's been a whirlwind tour of spacecraft shielding.
How the journey doesn't stop there.
No, it doesn't.
In our final segment, we're going to take a glimpse into the future, explore some of the cutting-edge research and concepts that could revolutionize how we protect our explorers for generations to come.
It's going to be exciting.
I can't wait. Until then, let's keep exploring this fascinating world of spacecraft shielding. And we're back for the final leg of our deep dive into the world of spacecraft shielding.
It's been quite a journey, hasn't it?
It really has. We've seen how engineers tackle those tiny but super fast micrometeoroids, figured out ways to keep spacecraft from turning into giant ice cubes or overheated ovens.
And explored some pretty ingenious designs, too. Like, who would have thought origami could play a role in protecting spacecraft?
Right. But we're not done yet. We're about to step into the future of spacecraft shielding, where things get even more, well, more futuristic.
Absolutely. This is where the really cutting-edge research is happening, pushing the boundaries of what we thought was possible.
Because, as we set our sights on even more ambitious missions like longer trips to Mars or maybe even permanent outposts on other planets, well, those hazards we talked about, they become even more of a threat.
Exactly. Longer missions, deeper into space. It all means we need to step up our game when it comes to shielding.
So what's in store for the future? What kind of futuristic shields are researchers dreaming up?
Well, one area that's generating a lot of buzz is self-healing materials.
Self-healing materials. Okay, that sounds straight out of like a superhero movie.
Right. It almost does. But the science behind it is real, and it has the potential to be a real game changer for spacecraft.
So what are we talking about? Spacecraft that can like magically repair themselves if they get damaged?
Maybe not magically, but pretty close.
Yeah.
Imagine a spacecraft hull that can actually repair itself after being hit by micrometeoroids or space debris.
So no more worrying about tiny punctures or cracks leading to, catastrophic failures.
Well, the idea is to minimize that risk significantly.
Yeah.
Researchers are working on materials that have these tiny capsules, almost microscopic,
Okay.
and they're filled with a special healing agent.
Interesting.
And when the material gets damaged, these capsules, they rupture and they release this healing agent.
Okay.
And then it reacts chemically and seals the crack or the
So
puncture.
like giving the spacecraft its own immune system, constantly patching itself up.
I like that analogy. It's a very visual way to think about it.
It is. And it's not just about, fixing damage, right? I mean, these self-healing materials could also like extend the lifespan of spacecraft, right? Making them more reliable and maybe even more cost effective in the long run.
Absolutely. That's one of the big potential benefits, especially for those long duration missions where sending a repair crew just isn't feasible.
Right. Like a mission to Mars, you can't exactly call a tow truck if something goes wrong out there.
Exactly. So building that self-healing capability into the spacecraft itself is really, really crucial.
I can see that. So self-healing materials are definitely on my wish list for future spacecraft. What other cool shielding tech is on the horizon?
Well, how about active shielding systems?
Active shielding. Okay, what's the difference between that and the passive shields we've been talking about?
So passive shields, like the Whipple shield, they just sort of sit there and absorb impacts, right?
Right.
But active shields would actually use sensors and actuators to respond to threats dynamically.
Dynamically. So they would be able to like detect an incoming threat and actually do something to stop it.
Exactly. Imagine a system that could sense a micrometeoroid heading straight for the spacecraft.
Yeah.
And then use a laser or maybe a small projectile to either vaporize it or deflect it out of the way.
Whoa, that sounds like something out of Star Wars, like a mini Death Star defense system for our spacecraft.
It kind of does, doesn't it?
It does. But is that even possible? I mean, that sounds like really advanced technology.
It is. It's definitely cutting edge stuff, but researchers are actively investigating those principles behind active shielding.
Wow.
And while there are definitely engineering challenges, to overcome, the potential benefits are huge.
I can see why. It would be especially useful for protecting against those larger pieces of space debris, right? Like defunct satellites or rocket parts. Those things can really do some damage.
Oh, absolutely. A Whipple shield is great for those tiny particles, but it might not be enough to stop a whole chunk of metal flying at you at thousands of kilometers per hour.
Yeah, that's when you need to bring out the big guns or lasers or whatever futuristic weaponry we come up with to defend our spacecraft.
Exactly. And active shielding could be the answer.
That's really exciting. But I imagine these active systems would require a lot of energy, right? And some pretty sophisticated sensors and computers to make it all work.
You're absolutely right. That's one of the biggest challenges. But as technology advances, especially in areas like miniaturization and energy efficiency, we're getting closer to making active shielding a reality.
Well, for one, I'm looking forward to seeing how that develops. It seems like, with every challenge we face in space, we just come up with even more more ingenious solutions. Speaking of ingenious solutions, what about those deployable shield structures we talked about earlier, like that origami shield? It just seems like such a smart way to save on weight and space during launch.
Oh, absolutely. Deployable structures have a lot of potential for the future of spacecraft shielding. And we're not just talking about origami anymore, although that's definitely a promising avenue. Researchers are also looking at inflatable shields, that could be packed down small and then inflated once the spacecraft is in orbit.
So like a giant inflatable bouncy castle in space.
Haha. Well, maybe not a bouncy castle, but the principle is similar.
Okay.
And there are also these modular shield concepts where you could have individual pieces that fit together almost like building blocks
Oh, cool.
to create a larger protective structure.
It's like a giant Lego set for spacecraft.
Exactly. And I love that because it means you can customize and adapt the shielding to different mission needs,
Right, right. That makes a lot of sense. So it's all about finding solutions that are not only effective but also practical and adaptable. It's a pretty amazing field.
It is. And what's really driving all this innovation? It's the incredible advances we're seeing in computational tools and simulations.
Right, because as these shield designs get more and more complex, you need more powerful computers and software to model them and to test them, right?
Exactly. Researchers are using artificial intelligence, machine learning, these high fidelity simulations that can actually recreate the harsh conditions of space right here on Earth.
Wow. So it's like giving spacecraft engineers their own virtual space simulator where they can experiment with different designs and see how they perform against all sorts of threats.
That's a great way to put it. And this is leading to a much faster pace of innovation in the field of spacecraft shielding.
It's amazing to see how technology is shaping the future of space exploration. But it's not just about the technology itself, right?
You're right. You're right. It's also about the people, the collaboration.
Yeah.
And one of the most encouraging trends is the growing emphasis on international collaboration and knowledge sharing in this field.
Because I mean, at the end of the day, space is for everyone, right? And we can achieve so much more when we work together.
Absolutely. Researchers and engineers from all around the world are sharing data. They're collaborating on experiments. They're pooling their expertise to develop the best possible shielding solutions.
It's a great reminder that, the challenges of space exploration are global challenges, and we're all in this together.
Well said. Well said. And as we look to the future, it's clear that protecting our spacecraft and the humans on board will continue to be a top priority.
Absolutely. From those self-healing materials to those active shielding systems to the power of global collaboration, it's a really exciting time to be following the evolution of spacecraft shielding.
It is. And who knows what groundbreaking discoveries, what incredible innovations lie ahead. Maybe one day we'll have shields that can withstand even the most extreme cosmic events.
It's a future I'm definitely excited to be a part of. And a huge thank you to you, our listeners, for joining us on this deep dive into the amazing world of spacecraft shielding.
It's been a pleasure exploring this topic with you, and we encourage you to delve deeper into the research, to keep learning and to keep that sense of wonder alive.
Until next time, keep looking up and keep those space helmets on.